Welcome to Mobycast. This is the fifth part of our release and remaster of the birth of NoSQL and DynamoDB. You made it. This is the last one. So in this final installment, Chris talks about the architecture of Viathan. It was the original internet-scaled database made by Chris's own pre-bomb company called Viathan. It's so cool to remember how we used to build things before the cloud. And actually what's even cooler is how it's not so different than how we build things today, and actually even how DynamoDB itself works under the covers, under the hood today. So now, join Chris Hickman, Rich Stats, our former producer, and me, John Christensen, for part 5 of the birth of NoSQL and DynamoDB.
Welcome to Mobycast, a show about the techniques and technologies used by the best cloud-native software teams. Each week, your hosts John Christensen and Chris Hickman pick a software concept and dive deep to figure it out.
All right, welcome, Chris and Rich, another episode of Mobycast. So, hey, Chris, this is the second time we've gotten together now after the holidays, and I never asked you what you did. Anything interesting over the holidays?
Yeah, it was really nice and relaxing. Got to steal away a few days down on the Oregon coast with the family. So,
beautiful.
Very, very, very beautiful area and very relaxing.
Excellent. How about you, Rich? What have you been up to? Or did you do anything interesting or fun during the holidays?
Yeah, I went back to New Jersey and spent time with my extended family. I'm pretty sure I didn't get out of sweatpants the entire time, which is usually the goal.
Excellent.
So yeah, it was good.
Cool. So we do Mobycast from our sweatpants as it is. So there we go.
Speak for yourself. I dressed up for this.
As for my holidays, I stuck around Eagle, Colorado, because this is the place to be during the holidays. Like, we're kind of close to the Eagle Airport. You can see the planes coming in as they go towards the Eagle Airport from our front window. And around the holidays, we just see that traffic pick up from a plane an hour to a plane every 2 minutes. So people were streaming in, getting ready to get their Christmas in the mountains on. And it was a good thing to do. It was a wet Christmas here in the mountains. Over the last 4 episodes, we've been talking about DynamoDB, and we are not done. Last week we got into, just the real detail of the physical sort of and logical architecture of DynamoDB. I guess really the logical architecture of DynamoDB, how the sharding works and what a storage node consists of, and the request router, the partition metadata system. And we didn't really talk much about auto admin except for towards the end. But this week we're going to kind of keep all that architecture in mind and go back and revisit where this all started, which is with the company that Chris founded called Viathan, and the company that he founded several years before DynamoDB was even a twinkle in Werner Vogel's eye. So, let's maybe, Chris, if you could just help me do a little bit better job of the recap, just in a couple minutes of where we were with the DynamoDB architecture. Go ahead.
Sure. Yeah. So with DynamoDB, we kind of called out the high level components, and those were the request router, that was the front end to the system. That was what all clients using DynamoDB, they're hitting that front end, and that request router is responsible for figuring out where the data is that's being requested to either be read or written to. Where does it live? Which storage node partition is it on? And so that was one of the other major components we talked about were these storage nodes, and these are those home partitions for all the data that's in DynamoDB. They're composed of 3 components there. They have the leader, the storage node leader, and then there's 2 secondaries, which represent the replicas. We also talked a little bit about the fact that the default behavior for DynamoDB is to be eventually consistent, so it doesn't wait for all secondaries to be updated before it returns back a response, although you can configure that to say that you do want it to be strongly consistent, but there's trade-offs with that kind of decision. We also talked about the partition metadata system, kind of like the routing tables, if you will, for DynamoDB, and given a particular piece of data, where does it live? And then you have AutoAdmin, which is their kind of integrated monitoring, healing,
repartitioning.
Just basically all that kind of housekeeping that goes on with kind of running a system like this that's so dynamic and where you do need to reshuffle things periodically. So they had the auto admin component. So those were the four primary components that we talked about with DynamoDB, and keeping those in mind will serve useful as we go into this next discussion about, okay, well, what came before that? What was Leviathan?
Great. And that all four of those things sound fairly complex when you just listen to their names, but it's really just easy. It's like you've got some data, you want to stick it somewhere. You got a lot of data, it's in a lot of different places. So you have request routers to get you to where your data is, and you have a partitioning metadata system to kind of remember where everything is. It's like you're for some reason I'm thinking of that whole idea of having a castle in your mind where you put it has different rooms so you can remember things, like, oh, I put this memory in this part of the castle. That's your partition metadata system. So yeah, let's move away from DynamoDB and roll back the clock a little bit and talk about the Leviathan architecture.
Sure, you bet. And maybe just a quick recap. We talked about this in previous episodes. If you haven't listened to the previous episodes in this series, definitely go back and do so. Before DynamoDB, in the late 90s, I was working at a startup, and we had the same kind of problems that DynamoDB had. The reason why DynamoDB came about, where how do you scale your database dealing with internet scale applications, and how do you have this virtual pool of just infinite storage that can be scaled out. So that was what that company was trying to do. We called this NoSQL database that we were building. It was the code name was Leviathan.
Just have to interrupt you, which remember is part of the whole Moby Dick theme of everything we ever talk about here at Calsys and Pro Docker training.
Indeed. So maybe digging into that a little bit. Again, it was really interesting for me. Whenever I see like the discussions about DynamoDB, about like what were the pain points, why it came about, what are the high level components, and then when I sat in on this deep dive during reInvent of like what's the architecture look like for DynamoDB, it's super interesting because it is really similar to the work that was done on Leviathan. And so just like with DynamoDB, we talked about the four main architecture components. We can also talk about, there's primarily four main architecture components for Leviathan as well. A little bit different, but pretty close. So the first one would be the API client itself. We'll get back to this, but in the Leviathan architecture, the API client itself is very much a key piece of the distributed system. Then
it's the front door to Leviathan.
It is. I mean, it's not. I mean, it was the API implementation. I mean, we were, this is late 90s, so things like RESTful APIs didn't really exist. The ecosystem wasn't there for kind of having like this same kind of like API driven development that we have now. So typically what you did is you built an API. It was a custom API, and you may have your own wire protocol. You may go over HTTP, you may not. And then you typically delivered that functionality via an SDK. And so that SDK was basically, client-side code libraries that someone that wanted to use this API, they would link in those libraries and get that code to use it. So that ended up being the way that we delivered our functionality, the way that folks would consume this functionality and hook into this storage system. And because it wasn't just an API, but it was also code, we could then, add additional put additional value-added functionality into it. So that's the only part that doesn't happen anymore, right? So, like even with HTTP APIs, I'm yet to meet a developer that isn't like, do you have an SDK? Is there any way I can not have to write all that HTTP handshaking logic and just use the SDK, please? But the part that we don't do anymore is stick much beyond just the communications into that SDK. Exactly. Yes. Yeah. And in our particular case, like we didn't really have a choice here. But So that was one of the key components. Another one we named it the update distributor, or UD for short. And this was a piece of the system that was responsible for handling write request. A third component was, we called it the base server, for lack of a better name. And this was really our storage node. And so this was basically where the data was stored. It dealt with everything else around it. So very, very similar to the storage node concept in DynamoDB. And then the fourth component is, we called it Shepherd. And Shepherd was our management system, the way of doing a housekeeping, the way of knowing when to do partition splits. It was responsible for migrating data when it had to, from one partition to another one and whatnot. So basically everything that managing state. I mean, it also kept track of the cluster and partition maps in our system. So when we talked about DynamoDB, they broke out their partition metadata system is separate from auto admin. With us, it was for the purposes of this talk, it was all combined into the one component, which we called Shepherd.
Interesting.
So those are the four key components. There's also some things that may come up during the rest of this conversation are some additional core components that we have, which were one we called Smart IP. This you don't need anymore because now we have things like elastic load balancers. But back then we didn't have that. So we came up with this term Smart IP, which was essentially virtual IP, a way of having a single way of addressing a cluster of resources and having the load balancing and being done across that set, and being able to dynamically change the set of nodes that are in that behind that particular IP address. So we had to build that ourselves. So we had that, and then another kind of core system component we had was, we called it our storage abstraction layer, or SAL. What this was a layer that was used by our base server, that storage node capability to have it interface with what was actually being used as the persistent store. And so we had this concept of basically abstracting that.
I'm a little confused by this. This is the one piece so far that I'm like, huh? What are you talking about?
Mm-hmm. So, this system and this technology went through many iterations. In the first iteration, the storage nodes we were using relational databases as the storage mechanism, right? So this storage abstraction layer, what it would do is it would make it so that it could speak a common language, and you could plug in, maybe Microsoft SQL Server or Oracle DB as your storage node, right? So that's what that was. Eventually, it grew to become even more capable, where it's not just talking to relational databases, but what about file systems as well. So that's what there was the recognition that the base server had some common logical features and component and functionality that it served, and that was irregardless of how it was actually storing it on persistent to disk or whatnot. So things like caching and the query engine, all that stuff was up in the base server level. And then when we had to go actually persist it out, then we went through that storage abstraction layer. I
just can't help myself. At the moment that you were building that part of your system is when you could have also been like, this company is now spending a great deal of money on a piece of the system that's not, it's like, what's the best way to put this in startup terms? You're building something and you don't have anybody using it. That's like in a startup, if you can't get people to use like the steel thread that goes all the way through, like, hey, here's the like opinionated version of this. If people are like not willing to use the opinionated version, then making each little piece like really super configurable probably isn't the solution. But I digress. Like it's just like, as soon as I heard that, I was like, oh my God, that's like a lot of engineering for a startup that probably didn't have any customers at that point.
Yeah, I mean, maybe kind of like paradoxically, it was actually probably cleaner to do it this way because it forced us to componentize the way that we were thinking about things, right? So like we could have had like just hard-coded Microsoft SQL queries littered throughout like the base server, but would that have gotten us? And we had like a few people on the team like that were like SQL experts, right? Not everyone was. So there were definitely benefits to doing that. And so it wasn't so much for the ability to go and support like anything out of the gate. It was, a lot of this was more for just architectural reasons.
Okay. I wouldn't let you do it. I'm just kidding. Anyway. I got to get off that. Like this is like a constant thing for me. Is like sort of over engineering that startups do. So that's why I was like grabbing on that piece. Let's just keep talking about where this what were some of the aha moments that were happening for you as you were sort of thinking about your old architecture and thinking about DynamoDB.
Yeah, and so maybe just dive in a little bit deeper into what those 4 primary components do. So again, the API client, in a way that you can kind of think of this is the equivalent of the parts of the request router in the DynamoDB system. So we didn't have that. Instead, because we actually had code running on the clients, we could include them as part of the actual system itself. And so things like the equivalent of the partition metadata, that was pushed into the clients. And what this gave rise to is that when they were doing read operations, they wouldn't have to go through an intermediary service. They could actually go talk directly. They would have all the information that they needed to go straight to the right base server. So kind of interesting, different. I mean, there's definitely pros and cons to it, but you are reducing. It's one last path that you're going through on the read case.
Was there a situation with that where different clients could get out of sync with each other and that be a problem?
Well, I mean, there's lots of consistency problems and synchronization issues, and like what happens if some state changes, and how do you get it distributed to all of them, to all the players in the system in a way that's safe and still meaningful. Absolutely, there are lots of pretty challenging problems throughout this whole system. But in general, without diving deep into all those various techniques, can say that for the most part, the simple case of like, hey, I got to go read some data, having the information necessary there to go get it, that was doable, and there was techniques and parts of the system that handled what happens when it did get out of date or whatnot.
Right. Well, I imagine that a connected client is kind of always saying, "Hey, let me know if the sort of map of where the data is has changed, and if it does, then it grabs a new map of where all the data is." And then if a client is not connected for a while and then connects, like that, it probably has to go ask for that before it's allowed to do any work.
Yeah, I mean, there's versioning, and there's there's a lot of event-driven components into this system, so that when changes do happen, I mean, this is essentially distributed caching, right?
Yep,
so
exactly.
Not an easy thing to do, but definitely solvable. And so that's really kind of what it came down. And a lot of times it's, you can't have a 100% consistent state, right, across everything. It's just impossible. There's just timing issues, right? Like, and so how do you detect when you are out of state, right? And how do you do the right thing? What happens when you're now have a cache conflict type thing? So all of that stuff had to be thought through and dealt with. And again, a lot of that functionality went into these API clients. So again, given that this was written in either C code or Java code, and there was the code to handle that in that.
That was going to be one of my questions. So was most of the Leviathan, was it mostly C, mostly Java, mostly C++?
Yeah, it was all C++ and really just using C++ as a better C. So not a lot of not tremendously object oriented, used classes sparingly where it made sense, and inheritance where it made sense. But for the most part, it was C code. The only Java code was for our Java based SDK. The Java API, right? Because we knew we had to support that out of the gate. We had to support.
Yeah, for sure. There's no question.
You're either running
2001
Windows,
Java, 1999 Java.
Mm-hmm. Yeah, it was either Java or Windows, right? That's what people were running. So we knew we had to support those two environments, and so Java was our answer also for Unix and Linux type thing.
Quick interruption to ask you to please go to mobycast.fm/show-notes and sign up for our show notes. Those give us a chance to send you the show notes once a week. They're detailed outlines that have all the information that we present in the show, which makes your email searchable. Really cool. And we definitely don't use that address to spam you. In fact, we can barely remember even to send out the show notes every week. So thanks for signing up. Right. That's pretty interesting. Yeah. And I guess I'm just thinking about the fact that, the big difference between DynamoDB and Viathan that we've talked about so far is the request router and partition metadata system living on the server versus living out at the edge. Mm-hmm. And it's just fascinating to me because that sort of back and forth just happens over and over. Like, one year it's better to push stuff out to the edge because you get better scalability and, less work for the servers to do. So a speedier little distributed system that you've got going. And then the next thing is like, no, but then it's hard to do updates and you can have out-of-date clients. And so let's do everything on the server. And then the next thing is like, oh, well, you can push out code from the server. So let's just do it that way again. And like, we can never really decide as a group, as a community, as software developers on really where the balance is best. And we keep like vibrating across either side of that balance.
Yeah. I mean, and it's just like technology in general, just the constant iteration and, different techniques, and there's technological advances and things like, bandwidth's changing and number of, CPU power is changing, and, the cloud versus on-prem, that changes things and whatnot. So it does, every time you go to design a system, right, it's not necessarily one right way of doing it. And, maybe, this year doing something, pushing it out and have it, on the edge, the work being done on the edge makes sense for your particular application versus, some other application because of some changes in, cloud or some new service that you have available to you. And maybe you don't need to, maybe there's some constraint that you can put into your system where it makes sense that you should do stuff on, the server side and keep it central.
It would not surprise me whatsoever if AWS did something like, oh, we've created a new feature of DynamoDB Smart Edge Processing, where they essentially push the request router and partition metadata system out to like greengrass edge type stuff. So like it can be even faster for, systems that are doing IoT or whatever. Mm-hmm. I wouldn't be surprised at all, especially because can't you already run DynamoDB locally? Isn't that a thing?
Yeah, you can run DynamoDB locally. It's that's mostly for
testing, right?
Testing and just development, right? But absolutely, with IoT and what AWS is doing with Greengrass, you also have Snowball and adding in its edge computing capabilities. Yeah. So, I mean, the things that can be done at the edge will be done at the edge, and usually almost always makes sense to do so. You just have to balance out, like, what's the overhead of doing that? So if you can make it so that there's very little state shared between these things that are out on the edge and kind of like phoning back home to a central data center, then you can scale out very easily. And you do want to push that computing to the edge and not have to do that computing inside your cloud, inside your data center. Mm-hmm. But when it's more of a bi-directional communication path, then you start running into a whole bunch of problems, right? Like it's now as you scale up, it becomes exponentially more difficult to handle that, and it becomes more complicated. So it just really depends on, your situation and what it is that you're trying to do, what the constraints are, what the access patterns are, to decide what's the best thing. For us, we had this is a good point, right? Because with us, this was very much kind of more of a closed system. So our clients were, again, these are heavy clients. They're going into application code for services that are consuming this storage service. This was a closed system, and you would have an instance for every network that you had or every data center that you may have had, right? It didn't really support the concept of this wasn't designed to be run as a service, software as a service type thing, and you wouldn't have multiple There were ways to do namespace partitioning to have multiple applications, but for the most part, I think this is each customer would have their own implementation, right? It wasn't one implementation for millions of clients out there,
right?
And so with that, having these thick clients that were active members of the distributed system, that kept that number finite, and so it's just it wasn't really an issue, right? We knew that there was going to be tens of these things or hundreds of these things. It wasn't with DynamoDB. DynamoDB is offered as a service, and you can have tens of thousands or hundreds of thousands of clients. So pushing state out into those clients that would be much more problematic.
Right. Yeah. And another thing you mentioned that you were able to do because it was a closed system is being strongly consistent versus DynamoDB's eventually consistent model. Talking about that.
Yeah. So this gets into that update distributor component. So we've talked about the read path. So because we have these thick clients and they have access to the metadata in the system, they can figure out which smart IP address for which storage server that they need to go talk to for the read pass. For the write pass, they went through this component called the update distributor, and this was responsible again for every mutation. So for every create or update request or delete, those requests would go through it, and its responsibility was basically to do the replication. So it was essentially doing a two-phase commit across multiple replicas. And so that's why our system was strongly consistent. This was just the design approach we took from the get-go, is that basically we would have this synchronous two-phase commit style replication of these write commands so that they would be replicated to at least two base servers, but it would do that all synchronously and then return back to the caller that now that write is complete. So that's why we were strongly consistent. With the difference with DynamoDB is with DynamoDB, they're doing those writes to the secondaries via true replication. So they're going. I don't know exactly the details whether they actually have if their actual storage node has code where it's doing the actual writes itself, or whether they're writing to logs and there's a replication component that's reading from the logs and then forwarding making those updates on the secondaries.
I would guess the latter, but yeah, who knows?
Yeah. But that was the approach that they took there. So
I want to interrupt you for just a second because you're talking about two-phase commits, and I'm just thinking about our audience. And one of the things I've noticed in the past 20 years is that there's less and less talk of transactions among developers for whatever reason. I just remember it being a constant theme of daily design and architecture conversations around the office from 2000 to 2005 or so. And then it's the whole idea just disappeared. We're not worried, I think it's because it all got subsumed into libraries and tools that people used in a way that was good enough that if you have to think about transactions, now you can count yourself among the senior developers. But yeah, can you just tell us what a transaction is and tell us what a two-phase commit transaction is?
Two-phase commits are basically just a way of implementing a transaction in a distributed system with multiple participants. So transaction just means something you're wrapping a sequence of one to n commands, and you want that all to run together as one unit. And so all of it succeeds, or if any one of those things doesn't succeed, then the entire thing fails and you don't change any state whatsoever, right? So
yep.
you could have a series of commands, like 5 different commands that you're doing. You could be updating 5 different pieces of data. maybe it's across like even 2 systems. So you want all that to happen as one atomic unit. And if it doesn't, then nothing should be changed. And so you have to have a way of reverting, if you will. Like if you're trying to, again, if you're have 5 commands and the first 3 commands succeed and then the 4th fails, well, then you have to roll back, right? So you have to undo what was done on those first 3. So 2-phase commit is just, it's a technique where basically it's just saying, look, hey, the first phase is going in and doing this update across all of the components. And then the second phase is getting back the response that, yep, that happened correctly. And then go ahead and committing it, if you will, to say now that this should be available now in the system. And it's now committed to the system.
Yeah. So phase 1 is like send out the work, have it all so that it all gets done somewhere else. And phase 2 is get all the acknowledgments back that the work was done and collect them all. Once you've got them all collected, then go ahead and lock it down.
Yeah. Mm-hmm. Yeah, exactly. So that's what our update distributor basically did. So it did that. And we actually had the concept where we weren't just, you didn't have to have just 2 replicas. You could have as many as you wanted. And so this allowed you to scale out for read operations, right? So we were very much interested in read performance. That was by far the dominant traffic coming through the system. So to go and have multiple replicas of your base server and allow any one of those to be read from, the more you had, right, the more your read throughput was. And if your write throughput was a small fraction of your read throughput, then the overhead of the 2-phase commit to go across n resources definitely was a good trade-off for having the multiple replicas for your increased read performance. And so that was the update distributor's job.
Cool.
Yeah, and then just I guess the last thing to talk in a little bit of detail would be that shepherd component. So this was one of the ones that the really hard discussions, this is where the hard problems were. And, how do you deal with these consistency issues? How do you deal with these timing issues and synchronous issues? How do you know who is what and who's the manager, who should be the leader, who's the master, as opposed to who the replicas, and how do you deal with failures and whatnot? So Shepherd, we ended up building this as there was a central service, but then we had agents. So it was also, part of it was an agent that would go on each one of the machines that was part of the system. There'd be the Shepherd agent running on it. So there was this bi-directional communication between them. So we had a separate management protocol, basically a control plane, if you will, for the system. And that was implemented through Shepherd and its agent-based architecture. And so Shepherd would give you an overall view of the system. It was what allowed you to add new nodes to the system or remove nodes. It would detect failures. It would be responsible for health checks. It handled all the metadata, the partitions, the clusters, and everything else associated with it. And then it did data migration, which was a pretty big topic for us as well to deal with. So whenever you had these splits that had to happen. So a partition got too hot, you needed to split it, and now you would have to move data from one base server to another one. And how do you do that in a way that's consistent and safe? It had functionality for that as well. Yeah,
right on. And while it's a shame that so much really good engineering didn't get much use, it is cool to see that that's the intellectual property that you created and registered with the patent office, got revisited and got put into, got essentially listed as the foundations of DynamoDB.
I was just saying, it would be interesting someday to, find out just, how much, if there was any cross-pollination there, if it was just kind of like serendipitous, like same problem space and similar solutions being developed type thing. So,
and it could be, like on the one hand, it's like, well, this is a really specific system, and it sure is interesting to see how closely the two are aligned. But on the other hand, it is, it's a very specific problem too. It's like, how do you get data and access it across many, many nodes efficiently? And, and it sort of does lend itself to a certain way of thinking about things. Yeah. I have a question for you though. Do you know when is the last time that Leviathan got booted up and run on a machine or multiple machines?
That was a long time ago.
I was wondering if you tried to give it a,
No, it would be so challenging to do so. It would have to be. This was all built on like Windows 2000, Windows 2K.
It was all Windows stuff. Yeah, that makes it harder. I think if it would have been just kind of pure, if it had been Linux stuff, it might be easier.
Mm-hmm. Yeah,
but the rate of change in the Linux, systems is sort of slower, and the backwards compatibility better.
Yeah. This is it was very low level system code.
Right.
I think we actually use some of the kernel APIs, I think, as well with NT, some of the undocumented kernel APIs. So it would be very challenging, but not impossible. I mean, source code is still here, and so like it's just a matter of the truth is I'm sure if you go onto AWS right now, there's an AMI for Windows 2K server. So
definitely.
Given that, and then at that point it's just you need the Visual Studio for the compiler, right? The Microsoft C++ compiler, and if you can get that, then like you're good to go and you can fire it up. But I think the last time that this was probably run was probably like 2001. Again, at Viathan, we went through some iterations and some different domain changes with this. So this was the first iteration of this technology, was using this adaptive partitioning architecture against using relational databases as the storage mechanism and really abstracting at the database level. We then took the same technology and repurposed it for file systems. And that became kind of like much more the focus. And that actually continued to live on beyond the company a bit as well. So we did that just because the friction associated with of adopting the technology was so much less with the file system, because there were no code changes that need to happen. We could provide basically our clients as like CIFS or NFS drivers. By doing so, it just became very easy for folks to now adopt this technology. So this ended up, and again, like I said, almost the exact same technology architecture and whatnot. It's just a different base server is really what we were dealing with. And basically you had a full blown like virtualized file system with infinite scale. And that was the next iteration of this technology for that company.
Interesting. So you built more or less EFS out of your Leviathan.
Yeah, it was more like S3 in that.
More like S3. Okay.
You could store a file, but also, yeah, I mean, it kind of similar to. I guess you're right. It was actually closer to EFS because that was the way that we hooked into it was through the file system driver. And we didn't want to require people to write code, right? So that lended more towards like, okay, this is just a big virtual file system.
It's your Z drive or whatever.
Yeah. The actual technology and the primitives were actually closer to what S3 does. But the way that it was adopted kind of felt more like EFS probably.
Super interesting. Well, I guess we should probably wrap it up, but this has been fascinating to talk about Leviathan and your history and DynamoDB and its future and how, 20 years on, they are still getting around to some of the features that you had built 20 years ago.
Yeah. It's been super interesting and fun for me to kind of look back and just be amazed by how much is just the same, like the same problems, and a lot of things haven't changed. So as fast as technology changes, like, and we've talked about this before in previous episodes, like it is cyclical, and there are certain patterns and techniques that do dominate. And I think this is an example where that's indeed the case.
Right. And I'm reminded of a conversation I had with you a few years ago, I think, where I was telling you about this company that I worked for or, did some contracting with called Taz. And I was telling you how they had one developer that decided to just do everything and see. And this was like, long after anybody was building any kind of web backends in C. But for some reason he was. And then not only was he doing that, but he had decided to build his own document database, despite the existence of Mongo at the time. And I was telling you how he had done sharding and had done some replica stuff. And I was like, why is he building all this? This all exists. And I just kind of remember you being like, mm-hmm. Yep.
and again, it's one thing to do like the base stuff, like to get the to handle like 80% of the situation handle the first 80%. Like you can just do that by like those main pieces, right? Like having things like sharding and some replication and the document portion of the database. But it's the last 20% that is so hard, right? And that's the stuff that prevents you from actually deploying and from actually like running, in some kind of available fashion.
All right. Well, let's leave it for next week. And next week, we're going to have a new topic. We haven't decided yet what it's going to be, but looking forward to talking to you again and hope everybody enjoyed.
Sounds good. Thanks, guys.
You.
See ya. Bye.
See you, Rich. Thanks for listening to that episode. You heard Chris Hickman, John Christensen, that's me, and you also heard Rich Statz, who was our original producer and the person responsible for the idea of Mobycast. We miss him, but we still work with him in other parts of our business. And also special thanks to our producer, Roy England. And we are real people that you can find and really communicate with, and we're available at mobycast.fm and also on Reddit at r/Mobycast. See you next week.